Okay, so we are all set. Let me share the screen. Okay. Can you see my screen?
Yes.
Okay, thanks.
Yes.
Great. Share sound. Okay, so the topic of today is model-based reinforcement learning, and we put in presentation mode. We'll start by touching very briefly the very basic approach, and then we'll discuss some state-of-the-art approaches that I think are the most relevant for the topic. So what is model-based reinforcement learning? So in model-based reinforcement learning, in addition to the standard loop that you have in reinforcement learning, you have an additional step where instead of using the experience just to learn a policy and or a value function that then allows you to act in the world, this is this branch direct reinforcement learning. The experience is also used by the agent in order to build an internal model, a model that the agent can use in order to plan and compute an improved value function or policy. So these two things, the use of a model and direct reinforcement learning, are not necessarily alternative to each other in the sense that they can generally happen in parallel. And specifically, this is what happens in one of the most famous standard reinforcement model-based reinforcement learning algorithms, which is DynaQ, which basically follows this loop where you have the environment in which the agent is interacting. And from this, the agent collects real experience, and this real experience is used in order to update the policy and value functions over direct reinforcement learning. And at the same time, this experience is used to build a model. And then this model is basically used in such a way that the agent can perform some sort of search or planning, and in general, perform simulations on top of this model, and then perform some updates to the policy and value function coming from the planning. So more in detail, if we look at DynaQ, the DynaQ pseudocode, we will assume a tabular setting, so where the model is learned in the form of a table, and we assume a deterministic environment. So this assumption basically allows us to store transitions in this table, assuming that every time we visit a certain state and a certain action, we will always obtain the same next state. Okay, so if the agent is executing something in some task in the world, the agent collects the state, executes an action by being, for example, epsilon greedy with respect to the Q function. And then the action is executed. We observe the new reward and new state, and we can perform an update of Q learning, which is the point D in this pseudocode. And at the same time, what we can do is, let me say, I say at the same time, but while this is assumed to be something that happens in parallel, of course, it's not like that. So it can be a sequential thing. So after performing a Q-learning update, we store the reward and the new state in our table, in our model. And then we repeat a certain number of times the following. So we sample from this from this table a state that has been visited. So we look at the table, we select one row, we get one state, and we also select one random action that was observed in this state. Then, given that the environment is deterministic, we know what is, because we have stored in our table the reward and the next new state. And basically what we do is we perform on this sample state a Q-learning update, except that now we're not doing Q-learning, but this is Q-planning, because it's called Q-planning just because the state is not coming from the environment. So if you look at this picture on the right, you can see that there is some difference in the number of updates that you can perform. So if you just operate with Q-learning without planning, then you can just perform one update at this state, for example. But if you have visited previously other states in the same iteration of this DynaQ algorithm, you can perform updates for all these states that have been previously visited. So this is a major improvement in the fact that you can more rapidly propagate the information coming from this last step that you took to all the other states. And that's the idea behind DynaQ. Now, this was one approach. Let's say that there are different ways model-based reinforcement learning can happen. So one way is we learn the model simultaneously to the interaction of the agent in the environment. The other thing that can happen is that you are given a model and still you perform some reinforcement learning internally to the model, and in conjunction with some planning algorithm. So, for example, what we just described for DynaQ would be this case if we removed the update to the model at every step. We assume the model is given. Now, there are many different ways of performing planning. We can do, for example, uninformed search, like depth or breadth first search, or we can do heuristic search. Now, a specific type of heuristic search that is typically used in this kind of model-based reinforcement learning algorithms is Monte-Carlo tree search. So what is Monte-Carlo tree search? Monte-Carlo tree search is a very simple algorithm that basically builds a tree of states and actions, and keeps stored also some information regarding the value of each state and action, so the Q function, basically. So let's say that we want to start our search from this state. Then we have a selection policy that belongs to the tree that typically can be, for example, the one that maximizes the Q function. So we select the action that maximizes the Q function in this state, and then we fall in this state that already is part of this tree, so we don't need to do anything. So we assume that we are not at the first iteration in this picture of the algorithm. So we select this action, we are in this state, we select again the action that maximizes the Q function, so on and so forth, until we reach this node, which is a tree where we did not yet try what are the actions that we can execute. Then when we are there, we perform an expansion step where we basically know that there are some feasible actions. We execute these actions, and we add to this search tree the node, the new state that is obtained in this way. And from this new state, we perform some simulations that are also called rollouts. So basically, we execute some other policy, which is not the selection policy. It can be a random policy or a learned policy or whatever. but a policy that brings us to a terminal state, or to a state where we decide that we can truncate our simulation. When we reach that, we look at the rewards that we collected through the path that was executed by this simulated agent during the rollout. So we look at the rewards, the collected rewards. We then perform some update in order to update the queue function at all the visited branches of this tree. Now, there are different ways to obtain a selection policy. The one that I say it was purely greedy with respect to the queue function, but one very famous version of the Monte-Carlo tree search, which is called UCT, basically relies on the upper confidence bounds formulation, where basically not only you try to look at the key function, but also at this additional term, which is c multiplied by the square root of the logarithm of n, where n is the visits to the parent, and divided by ni, which are the visits to the node. Now, what is this thing here? This is simply something that tells us that if you didn't visit this state too many times, you see, it's divided by the number of visits. So if this is high, then this term becomes very small. But if this is small, then this is higher. So if you didn't visit this state too many times, you are sort of encouraged to visit this state. Now, why did I talk about this? Well, actually, there is also the pseudocode here. Let's go first through this. Sorry. And actually, this is not even pseudocode, but it's some code that you can also find at this link, when I will put online the slides also for last time, which I will do right after this lesson. And so here we have the pseudocode. We don't necessarily need to go through it, but I also added a link here to a visualization of the Monte-Carlo tree search while executing. So let me show you what's going on here. So in this visualization, we are playing tic-tac-toe against a machine that performs Monte-Carlo. Here we'll select, I will say that human will start the game. So I select a certain action. Then here I can select the number or runs for the Monte-Carlo tree search. But let's say that I want to get a Monte-Carlo tree search action, and I can go step by step for the first few actions, and then for the first few iterations, and then I'll keep going and just get the action. So what happens here? So as I said, we are doing, this was the only node that was available in the tree. So we are doing an expansion because we are selecting an action. And from here, we perform some simulation using some policy where the outcome of this simulation, for example, this could have been a random policy. The outcome of this says the winner is the machine. Now, there is a backpropagation step, and values are updated. And then now this is the selection phase, where the agent says, okay, I want to try another action. So we do an expansion step where we get a new node added to the to the tree. And then we do another simulation, and then we do backpropagation, and then we are again at the selection phase, and so on and so forth. So this gives you a clear idea of how this works, and you can play with it yourself. So if you continue with these iterations, you will see that the algorithm will start building this tree that grows very quickly. You see? You see that it's growing very fast. And then we look at the last step, and we just take the action that the Monte-Carlo research says that is the most promising. Now, what happens at this point? I select another action, and we say, make Monte-Carlo research. You see what happened here? The tree that we computed before is completely discarded, and we are doing a complete new search. So from a new state, we do a complete new search, and we discard everything. So there are some versions of Monte-Carlo research that do this, some other versions that keep instead the tree. For example, many implementations of the UCT algorithm that I was mentioning before keep the tree also for future computations at new states, so that not everything has to be recomputed. And if you have questions about this stuff, and as I said last time, don't hesitate to interrupt me. So let's go back to presentation mode. Okay, great. So why did I talk about this? Because you probably have heard about AlphaGo, which was the first piece of software that mastered the game of Go, winning against the best human player in the world, so the champion. And in this AlphaGo algorithm, basically they do Monte-Carlo research with some reinforcement learning, and that's it. So, and of course, they have a lot of compute power, which we don't have generally, but the overall idea is really simple and at the same time very powerful. So I will start this video, which is a 5-ish minutes video that I think you should listen at quite carefully, because it gives some information that is relevant also for comparing AlphaGo with other algorithms that in past won at games like chess and so on and so forth. So pay attention. I think the audio should be shared. Yes. Okay. So, and if not, just let me know.
Until recently, computers have been relatively simple. Even the most powerful machines can only carry out the specific tasks they've been programmed for. This limits the scope of what they can do and how we can use them. After all, the real world is messy and unpredictable, and computers aren't good at dealing with that. But what if machines could think like humans? What if software could learn new things by itself? That's been a goal of scientists working on artificial intelligence since the very dawn of the information age, but it's proved a near impossible task. That might be about to change. A piece of software developed in London could just herald the biggest step forward in artificial intelligence and technology for decades. That software is called AlphaGo. It was developed playing simple computer games, and now it's about to take on the best player in the world in a Chinese board game called Go. A game of such complexity and intuition, no machine has ever been able to master it. AlphaGo's creator is the British startup Google DeepMind.
So the game of Go has just 2 rules, but out of those rules comes profound complexity. There are more possible board configurations in the game of Go than there are atoms in the universe. So really it takes a whole lifetime to master. We're ready now for the sort of next step for us, which is the ultimate challenge to take on one of the world's top Go players. So we've decided to challenge Lisa Doll in a $1 million 5-game match. Lisa Doll is the greatest Go player of the last decade, probably one of the greatest Go players of all time. I describe him as the Roger Federer of Go, and you know, the press and the excitement there is just huge from the general population because they really love technology and they love Go. Human professional players at the top of the game, you know, they're extremely creative and they'll do unexpected things that your own systems won't do. So we're pretty confident. Our internal tests are saying we should do pretty well. But Lee Sedol also, you know, he's been interviewed by the Korean press and he's very confident of winning. So it's going to be a very interesting matchup.
Of course, this isn't the first time computers have beaten humans in a board game. But what really marks out AlphaGo from the machines that mastered noughts and crosses in the 1950s and eventually chess in the 1990s is not just its ability to play a much more difficult game. It's the way it plays the game, by learning.
AlphaGo actually learns how to play in quite a human-like manner. So the way we start off training AlphaGo is by showing it 100,000 games that strong amateurs have played that we've downloaded from the internet. And we first initially get AlphaGo to mimic the human player. So we give it a position and we train it to predict the move that the human expert made. But of course, ultimately, we would like AlphaGo to be stronger than human amateurs and compete with the top professionals. So the way we do that is, after we take that first version that's learned to mimic human play, we then allow it to play itself 30 million times on our servers, and using reinforcement learning, the system learns to improve itself incrementally through it avoiding its errors and increasing and improving its win rate against older versions of itself. And after all these games, then you end up with a new version that can beat the old version, the original version, around 80–90% of the time.
The computer Deep Blue has tonight triumphed over the world chess champion Garry Kasparov. It's the first time a machine has defeated a reigning world champion in a classical chess match.
Deep Blue, Kasparov, after the move c4, has resigned.
This is in many ways a more interesting piece of software than Deep Blue, which was the piece of code that did beat Garry Kasparov back in 1997. Why are people excited at the moment? I think that's because these machine learning techniques have made a little bit of a breakthrough at the sort of lowest level of functionality that's really important for AI, which is perception. So being able to take raw data, large quantities of raw data, such as images or sounds, and to be able to do the basic processing and recognize what's there.
Key to understanding why AlphaGo could be a much bigger breakthrough than Deep Blue is to see just how differently the two machines work. Deep Blue was programmed to recognise the value of each piece on the chessboard. It then used raw computing power to search every possibility to work out which one was best. It's a bit like trying every password combination until the safe unlocks. But ask Deep Blue to do anything other than play chess, like even play a much simpler game, and it just won't know where to start. AlphaGo is different. Like a human, it can't measure all the possibilities in Go. There are just too many. Instead, AlphaGo teaches itself to play the game by watching thousands of others, playing matches against itself, and learning from its own mistakes. When historians come to write about the 21st century, I believe this match will be seen as a pivotal moment in our relationship with technology. Because as DeepMind software shows, we may be entering an age of thinking machines and general artificial intelligence capable of carrying out a huge number of tasks currently done by humans. And whether or not DeepMind wins the game, it's likely that intelligent machines are going to have a profound impact on the world around us.
So the outcome is clear. In the end, AlphaGo won the match, and so this was something that made news, and also was not expected to happen at this time. So that's one of the reasons for which it made the news. And we can simply look at what that was. So as it was described in AlphaGo is initialized with a neural network that basically is trained using supervised learning over millions and millions of training data collected from humans over the internet. And I mean, they just collected all this data and they trained this policy network in order to sort of imitate the human experts. So this is the set of features that the neural network took as input, and as you can see, they do not consist of just the image or just the white and black pieces on the board. There is some handcrafted human knowledge in here, where they basically build the most relevant features that are to be used by this network. And okay, this requires a lot of data, a lot of compute power, but still doesn't perform so well. What happens next? What they built out of this supervised learning policy is two things. One is the rollout policy, and the other thing is the reinforcement learning policy. The rollout policy is a policy that is less accurate than the supervised learning policy, but still very fast. So that's why they want to use it. So it's a much simpler network that is used in order to perform rollouts, the rollouts of the Monte-Carlo research that we just said. So this is something that needs to go very fast because the algorithm needs to be responsive and needs to perform this search quite fast. At the same time, this supervised learning policy is used to initialize the reinforcement learning policy. And you can see that basically this is how the supervised learning policy is trained, while the policy of the reinforcement learning is trained by doing policy gradient. So you see this is multiplied by z. This z is just the outcome of the match. So basically there is no reward at all during the game, except at the end when the machine wins or loses. So it gets a +1 reward or -1 reward if the agent wins or loses, respectively. So, and what happens? This policy is simply trained by playing against previous versions of itself. So there is this self-play that was described previously, where once the policy is initialized at the supervised learning policy level, then it starts playing against itself to start, and then it improves. It keeps one old version of itself, and time by time, this old version gets replaced by the newer version of itself. So this is not something that occurs every time, but every once a while. And together with this reinforcement learning policy, there is a value network. And let's see how these are used in detail. So if we look at the Monte-Carlo research that AlphaGo uses, so the phases are the usual ones. Here the selection uses this UCT policy that I was mentioning before, where we do not only maximize the Q function, but we maximize Q plus this exploratory term that is coming from upper confidence bounds, where if the action the action states are not visited so often, we try to promote the selection policy to visit them. Then there is the usual expansion phase, and then there is the evaluation phase. So the rollout phase, the simulation phase, where this is slightly changed in naming as in evaluation, because in the end, what happens is that the rollout which is executed is only one, while typically when you do Monte-Carlo research, you try a bunch of rollouts because you want to take into account stochasticity. In this case, they perform a single rollout, and so they obtain the reward at the end, And at the same time, they also evaluate the starting state of this rollout, so the leaf node, using the value function that is trained. So the value function is trained very easily, right, by just taking the mean square error basically between the value predicted by the network and the actual outcome, because the sum of the discounted rewards here is just really without discount factor, it's just the outcome itself. And what happens is that the final value of a certain state, which is used then for doing the backup phase here. So for computing this Q, we use this V, which is nothing else than a linear combination of the value coming from the function and the outcome coming from the execution of this rollout. Now, as I said, this rollout is performed by executing the rollout policy, which is a fast, responsive policy, which is less accurate. And you want that to be true because you want some randomization of your data in such a way that you can explore more. And this is the overall idea. Again, this is very simple. There is nothing particularly strange in anything that is happening, except that at the end, if you do this many times, you have a lot of compute power, you can obtain amazing results, as the AlphaGo algorithm achieves. Again, looking at this link, you will find the pseudocode of this. Is basically AlphaGo pseudocode, in the sense that it's performing Monte-Carlo research with self-play. So there is no there is nothing regarding the rollout policy and so on and so forth, the evaluation policy, the value policy, and sorry, the value network, and so on and so forth. But still, this is showing you more or less how things work if you want to try and play with this. So you can look on this web page, and you will find what is a starting point for you in order to implement this. Now, from AlphaGo, actually, there are several versions of AlphaGo. One is the AlphaGo Lee, which is the one that beat Lee Sedol, which is exactly the one in the green line. So this ELO rating is a score that is used in games. And you see that there is another version that came out after, which is AlphaGo Master. And then another major breakthrough was obtained by using Zero. So what are the main differences between AlphaGo in both these versions and AlphaGo Zero? AlphaGo Zero does not use human knowledge, meaning that there is no supervised learning policy network. So there is we're missing that supervised training phase. Another major change is in the fact that it doesn't use anymore handcrafted knowledge. And in that case, this means that it's trained really using just knowledge about black and white stones from the board as input. And another major thing is that this AlphaGo Zero version does not use two networks. So there is not anymore the policy network and the value network, but there is a single network that predicts some probability distribution for the actions and the value of the state. Another thing is that this version does not make use of rollouts. So there is the Monte-Carlo research here that is changing. So let's look at this a bit more in detail. So this is what we have seen before, which is AlphaGo, where we have all these usual phases for the Monte-Carlo research. And this is AlphaGo 0. So what happens here is that we do not, as you see, still we have the selection phase performed by doing UCT. And the expansion and evaluation phases are merged because we have the value network that is merged together with this probability distribution, action probability distribution network. And in the end, you do the backup without performing any rollout. We'll see how this training is performed, but let's focus for a second on what is this P and V that are coming out of this value of this network. So the V is the value, which is exactly the value, which is basically, in this case, a probability of winning. It's a representation of the probability of winning. And the P here is a vector of probabilities. So for each action, that allows us to determine what is the probability that the tree should be visiting a certain action compared to another one. So we can also look at the formulas over here. So the policy that is used by the algorithm in the end is computed in both cases in the same ways, which is by taking into account these counts of visited state, but the update for the Q function internally to the Monte-Carlo tree search is very different, as the value function before was updated by considering this linear interpolation between the predicted value and the outcome. So this was doing the rollout. Here we don't have that at all. And basically we're just taking this capital W that is sort of summing all the values for a certain, all the estimated values for a certain state in action, and then averaging, so dividing by the number of times this state and action were visited. And otherwise, the selection phase is the only thing that basically remains exactly the same. Now, how does this training happen if there is no rollout at all? Very simply, what happens is that so the agent keeps playing in self-play mode, and it will, as an outcome of this Monte-Carlo tree search, will execute an action, which is the most promising according to the policy, which is computed, as I said before, in this way, which is the same for the AlphaGo and AlphaGo 0 versions. So we perform display, we execute all the actions, we reach the terminal state where we get an outcome, win or lose. And what happens is that then this information is not collected, as we said, in the rollout of each MCTS, or which Monte-Carlo tree search, but it's just collected by executing the actual policy in the real world. So this is not simulated anymore. It's what is happening. And the outcome of the match is used then to update the value function and to also update the outcome is used to update the value function, and the policy as computed by this term over here is used to update the probability distributions predicted by the network. Why? Basically, what's happening here is that the network that is predicting the probability distribution of the action is being trained to basically sort of mimic this policy over here, which is the one that is used for the final actual action selection by the agent. So in the end, the loss here is that is used for training is a simple mean square again between z and the value function, and the cross sign should be between the probability distribution p predicted by the network F and policy pi computed as an output of the of this Monte-Carlo research. Then, in addition to this, there are some regularization terms, but we shouldn't focus too much on this. Okay, so up to here, we are at a point where we have a model that is given, and then we are performing some planning in conjunction with reinforcement learning. So we're doing some sort of model-based reinforcement learning because we're doing reinforcement learning internally to this planner and all of that. But the real version of the real version of model-based reinforcement learning comes with a new version of AlphaGo, AlphaGo-0, whatever, however we want to call that, which is called now MuZero, which not only learns to play at different games using more or less the structure that we have seen so far, but it also learns the model. So basically, this allows to this algorithm to also win at games like Atari games. And in fact, so why do I say this? Atari games do not have a clear state that is visible to the agent except the image or the RAM, which means that it's hard to plan on top of that because you don't have a proper simulation. But if you use model learning as well in conjunction with everything, then you can do this. Okay, so MuZero, how does it work? MuZero models the policy, the value function, in a similar way to what we have seen for AlphaGo-0. So there is a single network that predicts these probability distributions and the value function. And then it also predicts, models the reward and the new hidden state. Now, why do I say hidden state? As you see, from the observation that is being used by the agent, there is another function that emits this hidden state. You can think of it as an embedding, some sort of latent representation that is learned and that is used as the true, as if that was the true state. And then on top of that, in this latent representation, we have this f function that predicts the probability distributions for the action, the value function, and also another function, the g function, which predicts the new state and the reward, and which can be applied several times in order to, as you see in this small GIF here, in order to perform Monte-Carlo research, even if you don't have the simulation. So the simulation in this case is learned. So the simulation is obtained over the learned model and not anymore on the true model. So the Monte-Carlo research now still happens, but in this latent simulated model. Okay, so the training now needs to take into account also this piece of information. And so how do we train the model in conjunction with all of that? So basically everything that we said before stays the same, except that now when we unroll our policy, meaning that we execute our policy, we obtain our final outcome for the match, for example, in Go or in Atari games or whatever, we also in simultaneous we unroll the learned model. So in this latent space, we take the action and the state, the latent state. What we do is we execute this action, we pass this action and the state that we were in to this G function. We obtain a new reward and a new state, and then we take the action that was actually executed and we keep doing this. And basically, at the end, what we get is some error between the predicted state, latent state, and the actual action and the actual state that is then passed through the H function, right? So here we have a latent state that is predicted, and here from the action execution, we have an actual state from which we can, an actual observation from which we can compute a latent state. So here it's very easy to get an error, to compute an error, and so to compute a loss. And so this is the way we can also train our model. So this is simply now unrolling everything in parallel, and in the final information that we get in order to, the final information about the outcome that we get in order to update the V function. We use the policy computed by the Monte-Carlo tree search in order to update the probability distribution in the F function. Then we use the actual states that are the actual observations that are obtained and then parsed through this embedding function in order to compute the error and improve our learned model for the prediction of the next state, and similarly for the reward computation. And so this closes this part regarding the AlphaZero, AlphaGo-0, MuZero, everything part. But take into account one thing. As I said, MuZero is capable now by doing this or also playing Atari games. It doesn't achieve performances comparable to Agent 57, but still it's capable of achieving, I think, superhuman performances on 51 video games, if not superhuman performances, but anyway, very good performances on 51 video games. Still, there are some that doesn't play well. So again, Agent 57 is the first agent that wins against over all the 57 Atari video games achieving superhuman performance, but still MuZero is a very important step in that direction. Okay, questions before we move on with this discussion, which is anyway related to what we just said. Questions on this? If you ask questions in the chat, it's not ideal anyway. In case, just unmute and talk. What's happening here? Okay. Assume there are no questions. So in this MuZero model, we have said there is a model that is learned in this latent space, and this is not so uncommon. So there are other papers that do this. For example, in this paper, learning latent dynamics from planning from pixels, the authors are doing exactly the same thing. So here is we're just connecting what is happening in MuZero to what you can do also in other environments, and what you can do also for eventually controlling some more complex agent in continuous space. For example, in this paper, they assume that they not have access to the internal state of the simulation, but they only use pixels, so images corresponding to what is an observation of the state of the agent. But again, we do not have access to the actual state. So this is a partially observable macro decision problem. And the idea here is that if we learn a complete representation, then we can use that for planning. And in order to do this, given that we're dealing with partial observable Markov decision process, we need generally a recurrent model. And then when we do this, we can plan in this learned latent dynamic space exactly as MuZero was doing. So here there is some notation where basically we have the transition function, the observation function, and the reward function, then the policy that we know that is now computed as a function of the observation instead of the state, because the agent doesn't have access to the true state. And in these papers, the authors propose an approach that is called Planet, which learns the transition model, and they also learn the observation model and the reward model. So this is similar to what is happening in MuZero, except that the observation model here is trained as well using this specific way of doing it that we'll see. So the policy also in this case is obtained entirely using planning. So there is no policy network even in this case. Also in MuZero, there is not a policy network, but there is a policy that predicts the probability distribution for the actions, right? In this case, we don't even have that. So the policy is obtained using planning, pure planning, in an MPC fashion. So what do we mean in MPC fashion? MPC operates in a receding horizon fashion, meaning that we are in a certain state, we perform the planning at the horizon that we want to cut the planning. And then after we do that, we do not use the action for all the actions computed, but only the first action, and then we discard everything else. Okay. So Planet operates in the following way. So very simply, there is this model fitting and data collection steps that are generally separate, as in many reinforcement learning algorithms. So let's look at the data collection part that is basically the same that we have in every reinforcement learning algorithm, except that instead of using the reinforcement learning policy here, we use a planner. So we start by resetting the environment. We operate for a certain number of time steps until the termination or until we decide to stop. And from this, given the observation, we infer the internal belief. This internal belief is computed by using this encoder here, basically, so which is again similar to what MuZero does. And then we use the planner to compute the policy, and we do this in this MPC fashion. And more specifically, the planner that is used in this algorithm is called cross-entropy method, which is nothing else than a population-based optimization algorithm that gives us the distribution of the action sequences that maximize the objective. So similar to what we do generally is we add some exploration noise to the action, and then we execute the action, and we collect new information, and we add them to this experience replay buffer, to the replay buffer. And then for fitting the model, we just sample from this replay buffer uniformly, and then we compute the losses, and we update our model parameters. As you see here, in order to perform this planning, the algorithm encodes past images. So these are the past images that are encoded and used to basically start all the computation of this recurrent model that needs to unroll by taking into account the actions, but also the past states which are obtained in this belief space, in this latent space, again, by looking at all the images, so the observations, and then just unrolling this model. So here there is some videos regarding this approach. There's, I don't remember if there's some audio here, but anyway, they show how the planet approach is capable of obtaining some good performances, and which you can see also from these plots can be much better even compared to some state-of-the-art model-free reinforcement learning algorithms. So you see here the progress over training of this approach. So what do we mean here? Basically, what is changing? The planner doesn't change, so it's always the same. What is improving is clearly the learned model, which is then used by the planner in order to compute the actions. So more or less after 2,000 episodes, you see the algorithm is capable of achieving very good performance. Okay, so as I was mentioning before, if you look at these plots, you will notice that here we have some lines that are showing us what are the performances achieved by obtaining by using state-of-the-art algorithms like A3C or D4PG. These are model-free algorithms. So D4PG sets always an upper bound for this algorithm, and more or less A3C sets a lower bound for the algorithm itself. And you see that Planet is capable of achieving very good performances, sometimes also performing better than D4PG. However, you will notice here that there are these two items, purely deterministic and purely stochastic. This is telling us that the model that they are using in the paper, they explain that they use a hybrid between deterministic and stochastic models, because if you only use deterministic or only use stochastic models, basically these are the performances that you get that are not so great. So you need to mix them in order to achieve good performances. Okay, so moving forward, what happens now? Now that we have our model that is, so there are two things that we need to think of. One is, this is the case, like in this scenario where we have been doing this kind of training in the model, but unfortunately, doing this on robots, for example, is basically impossible, because if you need your robot to execute a policy and crash itself on the floor or whatever, this is not doable. So what happens generally is when you have to do these kind of things or perform this kind of trainings, even model-free reinforcement learning trainings, you generally use simulators. So you use some model somehow that exists, but it's not so accurate, in the sense that it can be as accurate as you want, but it's not corresponding to reality. So as you will see here, there is a gap between what happens in simulation and what happens in reality. I think this is the wrong video. Give me just a second. I'll find it back. Okay. Let me share again the screen. Okay, so this is the correct video directly on YouTube. So in simulation, they learn using reinforcement learning this controller, but if they transfer the controller as it's learned directly to the real robot, it miserably fails just because there is not enough accuracy in the model. Now, with an improved model, as they say, as they called it, they're able to reproduce the behavior trained in simulation also on the real robot. And this is called the sim-to-real approach. Now, there are several ways of performing sim-to-real. This is one version of doing that. So the version that they are using will describe it right after this video. But in general, you can perform sim-to-real in many ways. Okay, I think we can stop here. What are these ways of performing sim-to-real, which means narrowing the reality gap, the gap between simulation and reality? One is performing fine-tuning. So, for example, if you train a policy in simulation, then when you deploy that on the real robot, as you know that it is not so bad and it's not going to destroy the robot, you can continue doing the training and performing fine-tuning. It's called fine-tuning exactly because you already start from a trained policy. So you do fine-tuning on the real robot. Another approach that we'll look at is using progressive networks. The approach that they use in this paper is a mixed approach between improved modeling and randomization. So they improve a lot the simulation by performing some system identification, improving the models of the actuators and the delays, modeling the delays that there are in the real robots, so on and so forth. But also, what they do is performing some randomization, so applying some random perturbations to the controllers, for example, or to the controllers to the actions, and at the same time also performing some randomization in the dynamics parameters. So we'll now look detail at progressive networks and some randomization, mostly at a high level. So what are progressive networks? Progressive networks are something that was introduced in literature in order to avoid catastrophic forgetting. So how do they work? Let's say you train your neural network, for example, on a certain task, this task, which is playing this game. Now, you would like your neural network to be capable also playing another game without having to learn everything from scratch. So you want to add another task and perform some multitask training, at the same time transfer some knowledge from this task to this other task, which is another video game. So there is probably something in common. And how do you do that? Basically, you add new parts to the neural network. So you add this new structure here, which is a new neural network. But in addition to that, you also connect the layers of the previous network with the one of the new network. So now training in this case doesn't happen in the old network. So these weights that connect the layers of the previous network stay fixed, while the weights that connect the old network and the new network, as well as the weights that connect the layers of the new network, are not fixed anymore, so that they can be trained. So basically, this allows us to avoid that this network forgets the information that it has already. So these weights stay fixed, and in this way, the policy continues to be good in order to play this game. But at the same time, this information that is encoded in each layer of this policy, for example, is transferred over these connections to the new network layers. And this is why you perform training over here, because we don't know how much this information is important for the new task that the policy is executing. So that's why these layers are frozen and these one are not. And of course, the layers of the new network are not. And you can do this several times. Like, for example, in this picture that you see, we have already added two networks in which two tasks, and we are adding a third one. So where now this and this weights stay fixed. The weights that connect the first network and the second network stay fixed as well. But the weights that connect the first network and the third network, as well as the second network and the third network, as well as the weights of the internal weights of the third network, are not fixed. So is this clear? Okay, so if you now assume that you perform performing training in simulation and learning to execute a task in simulation is a very similar task to the one that you would do on the real robot, then you can basically do the same thing. You want to do some transfer learning. You want to transfer some features and some knowledge collected in simulation to the real robot. You don't want this agent to start from the scratch on the real robot. So you can use basically this progressive network approach to learn to execute the same task on the real robot, knowing that there is some difference between simulation and reality. And at the same time, you could also teach the robot to do another task B without starting from scratch. So this is a small video showing exactly the learning simulation. So the goal of this robot is going to this red object. And this is on the real robot. Okay. So this is one way of doing things. And if we compare that to fine-tuning, which is what they did in these papers, you will notice that apparently progressive networks appear to be more promising compared to simple fine-tuning. I guess this is true for several reasons. Also because the experience that you collect in simulation doesn't get, I mean, the network doesn't forget that information. And this is one reason for that. At the same time, the other powerful thing of progressive networks in comparison to fine-tuning is the fact that you can use them to learn also other tasks that are not the ones that the policy network was trained on initially. But anyway, so if you look at these plots where the trials are sorted by decreasing final rewards, so it's a bit unusual, but they sort them in reverse orders, you will notice that progressive networks typically obtain higher final rewards in comparison to fine-tuning. And this is true when there are many different changes that occur between simulation and reality. So for example, here there are changes that are subtle perspective changes. If there are significant perspective changes, this is true as well. If there are color changes, this is not always the case. So there are many trials in which the fine-tuning goes better than progressive in this example. And if there are significant color changes, however, a progressive network appear to work better as well. So this is a comparison between fine-tuning and progressive network on these tasks, for example, on a robot that needs to reach an object. Let's see now how this performs, how dynamics randomization performs on a similar task. And for this, I will let the video say what we need to say. So as we said, we don't perform training on a real robot because it's just too inefficient. It requires too many data. But in simulation, it's okay. So domain randomization here is realized by changing the parameters of all of these terms, so the mass, the friction, and so on and so forth. This is in simulation the push task, where the robot has to push this object to the specified location. And this is learned using more or less standard reinforcement learning algorithm using a recurrent neural network. And this is in reality. So what is happening here is pretty straightforward. Again, in the training, during training, there are few parameters that represent basically our dynamics model, and parameters like mass, friction, and stuff like that, you can change them in such a way that basically your learned controller is much more robust to differences in the actual embodiment of the robot compared to simulation. Basically, what we're doing in expectation, this using these randomized parameters, we will find something that is similar to the scenario that the real robot has to deal with. So if you don't do randomization, you see how it fails. So you also see a comparison between using the recurrent network in comparison with standard feed-forward policy. And this is, of course, there is some more difficulty for the feed-forward policy, also because we are trying to learn over a variety of parameters that are basically unknown to the agent. So in fact, what's going on here is it's not exactly a POM-DP, but similar to POM-DP. Okay. And basically, this concludes the set of slides that I have prepared for today. So I would like to give you some space for questions if there are. Any question? No. Okay. You are a very silent group of people. But anyway, were you trying to say something, Roberto?
No, I had no questions.
Okay. Okay. Sounds good. I hope it's not because everything was confusing and not clear. But anyway, given you don't have questions, then I have concluded my